Hey guys, so welcome to the first lab video of the semester, and welcome to the mechanics lab. If you've never been in here before, it's kind of a nice little space, a lot of room for all the students to normally come out and watch these labs being performed. We would only be in this lab anyways for one lab. The other ones will be in the building 50, I think. But the center point of this whole room is this machine here behind me called the Universal Testing Machine, or UTM. It's a very, very, very popular machine. It comes in all different types of loading capabilities and testing capabilities. And the goal of this machine really is just to test materials. So in testing materials, we can either apply a compression load, a tension load, or if we maneuver the material so it is in a beam setup, then we can apply flexural loads. So the UTM just in itself here comes in two parts. So we have the RAM, the loading RAM right here, and the sample is going to go right in there, and you'll see that here in a second. And then of course we have the hydraulic system and then the readout. This is a nice system here because we have a big old display that normally you can see the test and the results coming in real time. So for this week, we're going to be doing the uniaxial tensile test, and that's pretty much just pulling these several materials or several types of metal in one axis, uniaxial, and then we're going to be measuring the stress and the resulting strain from this device in itself. So these loading arms can actually record the strain just by the movement of that. However, this is assuming that these loading arms are moving at the same rate and the same displacement as the material. Now we know that these loading arms are not going to be perfectly attached to the material. There's these little teeth that grip onto the material, and there's going to be some slippage between the teeth and the friction on that with these material specimens that I'm going to show you here in a second. To overcome that, we use what's called an extensometer. And this extensometer is a LVDT, just like we went over last week's lab. And basically what that does is allows us to accurately record the strain occurring on the material itself, since that's what we care about, and not necessarily the strain in the UTM, which may not be the most accurate representation. Okay, so I'm going to set up the material now. Remember, we're doing 3 materials for this lab. We're doing steel, aluminum, and a cast iron. And you'll see I'll just set up one, and then we'll go over the actual loading rate, and then we'll start breaking some material and getting the data for our stress strain curves. Okay, so next material we're going to test is cast iron. Now cast iron is much, much more brittle than mild steel, what we just saw. So failure is gonna happen pretty quick. We're not gonna see that necking like we saw last time. Look for it down somewhere in this edge. For some reason, this cast iron likes to fail down here. And remember, it's gonna just happen really quick because it's brittle. Okay, so I was completely wrong about where the cast iron was gonna fail. Usually it's at the end, but whatever. You could see hopefully that it was a very brittle. You didn't see much elongation like we saw in the mild steel. You guys get the point. So next up, we're going to use aluminum. This little sample. Aluminum's really light, really expensive. Also, it's hard to weld and stuff. So, but super light, and we're gonna see how it fails here now. So that's it for the Uniaxial Tensile Test lab. Hopefully that helped a little bit. Just get a perspective of what this test would look like in person. This is the samples here after they've been broken. So this is the steel, this is the cast iron, and then this is the aluminum. And what you guys can probably see right off the bat is the amount of elongation we see in the aluminum and the steel, but we don't see in the cast iron. Remember, the cast iron is considered a brittle material, so that has, even though it has a higher strength, it doesn't deform as much and it fails much more abruptly. We also see necking occurring in the steel sections here and the aluminum. And we don't see that here as well. So that means that the steel and aluminum are more ductile because they allow more deformation before they break as well. So look through the data and create those stress strain plots for each material, and then try to characterize the ductility and the brittleness and the toughness following the lab instructions. One more thing to note too, the extensometer, for whatever reason, was not working. I don't know if it was calibrated correctly or not, but the data doesn't make sense at all. So I'm not providing any extensometer data, and you probably will notice that in the spreadsheet. And we will see some contributed errors in our data because we don't have that extensometer. You might notice the stress strain plot will first start curving up instead of going straight to the elastic region. That's because of the slipping in the ram right over here. So that slipping in gripping the material, you can see here, there's those little grip marks. Those grip marks are because the machine is trying to hold on by friction, and it's not going to be a perfect bond between the materials. So that's going to be your major source of error in this. Make sure to follow the lab report and look through all the requirements on there, and good luck this week, and let me know if anything comes up or you guys have any problems.